All right, welcome back. Dr. Pitcher here, and in this lecture, we're going to take a look at the hydroxylation of alkenes. Now, what is a hydroxylation? A hydroxylation is, we have an alkene and we are adding two OH groups. So it's not a simple hydration where we're adding water. We have a total addition of H2O2. So that means we actually have a net addition of one oxygen because we have H2O and then we have another oxygen to make it H2O2. So this is an example of an oxidation. Adding H2O, like in a hydration, is neither oxidation nor reduction. We're adding both H2 and O, so we don't have a net addition of either one. They basically, adding H2 would be a reduction, adding O would be an oxidation, and the two cancel each other out. But in the case of a hydroxylation, because we do have this net addition of oxygen, this is an oxidation. Now, there's a couple of ways that we can accomplish this. First method is by generating an epoxide. And how do I want to describe that? Well, we'll just call it epoxidation. And let's go ahead and take I'm going to use a cyclic alkene here. And I'm going to use something called MCPBA. MCPBA is meta-chloroperbenzoic acid. Okay, it has the following structure here. This is a peroxy acid. We have an extra oxygen, so it could be written as RCO3H. So any peroxy acid will work. MCPBA is a typical one that's used. And the result of this reaction is the formation of something called an epoxide. And what an epoxide is just a three-membered ring with two carbons and one oxygen. Now, I'm not going to require you or not going to hold you responsible for the mechanism for this reaction, but I just want to go over it briefly. We'll go ahead and have our alkene, and then our peroxy acid, HOO. So here R would be the benzene ring and the chlorine. And excuse me, we will get, let me draw in some lone pairs here. We'll get pair of electrons from the double bond attacking the oxygen there. This bond will break and actually go to form a new carbon-oxygen double bond. Of course, now we need to do something because we can't have 5 bonds on carbon. Those will pluck off that hydrogen, and these leftover electrons then will go there, and that gives us now our oxygen. And notice that this is similar to the bromonium ion and the mercurium ion. I always forget what that's called. Anyway, the one that you see in the oxymercuration, demercuration. All right. Now, this is just epoxidation. So we've made our epoxide here. And what can we do with the epoxide? Well, we can open up the epoxide ring. And it would be something like this. We'll have our epoxide here. And then we will either treat this with some aqueous acid. So we'll do H3O plus or OH minus, so sodium hydroxide. And we will end up getting now the following dihydroxy species. So now we've done our hydroxylation. Notice that this is anti-stereochemistry. Now, I actually really like the mechanisms for this reaction. I think they're pretty cool, so I am going to show them to you. I'm not sure if I'm going to hold you responsible for them at this point, because we'll look at them again later on. Then again, I might. We'll see how things go with this chapter, and I'll let you guys know. But let's look at the mechanism of acid catalyzed epoxide ring opening. All right. So we'll start out with our epoxide here. And then we'll have our H3O plus, our aqueous acid. And what's the first thing that is going to happen? Well, an important thing to remember is that when you've got acid present, you're probably going to protonate something. Okay, so you're going to protonate whatever kind of Bronsted base is there. And so let's see, what can we do for a proton transfer? Well, let's do that. A lone pair from the oxygen will pluck that hydrogen off. And now we will end up with the following species. Lone pair, positive charge. And H2O there. Now, water is a nucleophile. It's just not a very good one, but it can be a nucleophile. And we have a highly strained system here. And the fact that we now have a positive charge on this oxygen means that it's much easier to get this, this ring to react. If we just tried to have water attack one of these carbons, it wouldn't work because we'd end up with a negative oxygen as a product, and we're not going to have that if we have acid present. So we'll go ahead now and have our water attack, and so it comes in from underneath. If the three-membered ring is, is sticking up, then the water is going to come from underneath, and then those electrons will be kicked up there. And that will give us now the following. We will have this guy will be up, and then we'll have OH, H, lone pair, positive charge. And now another molecule of water can come along. Again, this is, as I said, aqueous acid. And we'll have a final proton transfer, and that will give us our final product. Now, we could have attacked at either of these carbons, and if we attacked at the other one, we'd end up getting the enantiomer. Now, there's a couple of things to note here. One is that when you open in acid, you're going to add the water to the more substituted. So, well, I'll summarize that later, I think, actually. Let's look at the mechanism of the base-catalyzed epoxide ring opening. And I should add in that we do need water present. So H3O plus means aqueous acid. We've got protons, we have water, it's H3O plus. So we have plenty of water. We need, in addition to OH, we need to have water present for our, in our base catalyzed version. So let's draw the epoxide. And now I've got my base, and I've got a negative charge, so I'm not going to be doing a proton transfer first. This is a good nucleophile, so I could go ahead and I could have nucleophilic attack, popping open the epoxide. Give me that, and then OH. And now I've got water present, as I mentioned before. So I can pull a proton off of the water, and that now gives me my final product here, OH and OH. And again, we could have the OH minus attacking the other carbon, and then that will pop open the ring the other way, and we would get the enantiomer. Now, both of these, whether it's acid catalyzed or base catalyzed epoxide ring opening, both give the anti-stereochemistry. The two OH groups are anti to each other. So we get a trans product here. Well, one area where they differ is the following. So let's say we had, let's say we took this and we treated this with MCPBA. I would now have I would now have the following epoxide. And then if I open this in H3O plus, I'm going to get my it's going to attack at the more substituted, so I'll end up with an OH like that. That guy kind of flips over, and then that pops open, and I get OH, H there. Okay, so in acid attack, we'll say nucleophilic attack at more substituted carbon. Compare that to NaOH and water. And now we'll actually get attack here at the less substituted carbon, which will give us now popping open like that. And we'll still have the methyl group will still be in the down position there. So in base, the nucleophilic attack is at the less substituted, the less hindered carbon. Okay, when we've got a weak nucleophile, we need to activate this oxygen by protonating. That's what we did here. So now that's more reactive. But just like when we were looking at the halohydrin formation, and we get the water adding to the more substituted carbon for electronic reasons, there's a better stabilization of a partial positive charge there. That gives us our product in acid. In base, however, OH minus is a good nucleophile, and so it attacks the less hindered, so there's no methyl group to kind of get in the way. The OH minus attacks the less hindered carbon. So just something to remember to file away. And, you know, if you happen to get that bit of regiochemistry wrong, that's not the end of the world. That's a rather minor thing. You know, as long as you know that you've got the anti-stereochemistry when you're opening up an epoxide, whether it's acid or base. Okay. Now, there are some other ways we can do some syn hydroxylations. So let's go ahead and take our prototype here. Not really prototype, but I can treat this with osmium tetroxide. And is this 2 steps? I'm just double checking here. Yeah, I just want to make sure I've got the right reagent here. So I believe the text uses NMO, but I'll double check that, which is a co-oxidant here. And what we end up getting is the following. We have our syn dihydroxy species. The other thing we could do, if you don't want to use osmium tetroxide, which I don't blame you if you don't, this is nasty stuff. This fine powder, you don't want to breathe it in because it will kill you. And I actually think it's toxic at levels lower than what you can actually detect by sense of smell. So yeah, bad stuff, nasty. So why don't we do this? Let's do KMNO4 and cold and dilute. That will give us the same result. Perhaps a little harder to control because permanganate is actually a very good oxidizing agent. And you know, if it's too warm, if it's a little acidic or basic, we may get an actual oxidative cleavage, which we'll talk about in the next lecture. All right, now what does this mechanism look like? Well, I'm not going to go through it all, but I just want to show you that you get at one point the following species. Oh, and I should mention OSO4. What does that look like? There we go, osmium tetroxide. There's my osmium tetroxide. So my OSO4, when it reacts, two of the oxygens will react with the double bond and they'll make this five-membered ring. And this is a species, I believe the text calls it a cyclic osmate intermediate. And then this ends up then getting reduced to the final product. And I believe that this is where the NMO comes into. This is where the NMO enters into things. You could also use something like sodium bisulfite, NaHSO3 is something else you could use. Yeah, I'll double check and see if there's some other reagents. So again, I'm not going to hold you responsible for the arrow pushing for this mechanism, but I want you to understand what's going on here. Similarly, with the permanganate, and let me just try to remember, I think permanganate has, hold on, let me check here. Where is my permanganate here? KMNO4. It doesn't show it in the McMurray text. So, I could just draw it and then go back later and correct it for you guys, but I do want to get it right the first time, and I always kind of forget how many bonds we end up having on the KMNO4. So yeah, that would be an O minus here. O minus. You don't actually isolate this, so let's just go ahead and put that in brackets there. And And then this gets further, again, then that will be further reduced to the, or will then get reduced to the dihydroxy species. Okay, so these are, as we've seen, some additional reactions. And you know, I hope that you've noticed some of the similarities with other reactions that we've looked at this chapter. The epoxide ring opening. Well, gee, that's just like opening up the bromonium ion. Synhydroxylation. Well, gee, that involves adding two things to the same side of the double bond. So that's like the hydrogenation, or like the hydroboration oxidation. We're adding things to both sides, or both things to the same side, or same face, I should say. All right. I think that's enough for this lecture. It's gone on a little bit. In the next one, we'll look at what happens if you use hot KMNO4 and perhaps some other reagents, and we'll actually really tear apart some double bonds. Anyway, until then, stay safe. Bye now.